and close to the teacher, you're too scared to fall asleep.
No, it just doesn't work like that. I used to fall asleep on the first desk of the lecture auditorium. Evgeny Vladimirovich Dashkov remembers.
Он, наверное, будил тебя своими
Не, он вообще спокойно, мы с ним общались после этого прекрасно.
Do you know Evgeny Dashkov?
Never heard about.
You're just on the same boat with him there.
But be careful.
Everybody knows everything
I will cut
about
the
us.
first part anyway. Okay.
No, we all love Evgeny Vladimirovich.
we are the lost generation. We are like the last ones who studied on software engineering while it was the old program. Now people
okay,
study like completely
History
different
of
programs.
Russia.
History of Russian, что-то там, короче.
I mean, I think there are some positives to the new program.
Yeah, of course. But
The Java course has upgraded, as far as I know, software construction.
Also, the lectures on the first.
20 years ago, I had to learn Java. I never used it in my life.
no,
Just C++. I should know. I regret not learning because I wanted to make grader in C++ for you.
now they study like assembly language, C, Java, algorithms, data structures, and mathematical analysis, linear algebra, correctly, all this stuff. Now, it kind of seems better.
But you didn't have algorithms course.
Yeah, we had. It was kind of screwed up because they had to change the professor in the midst of the year.
A lot of things. Yeah.
Also, I think for the first month it didn't start.
The guy just
because
didn't come to the lectures.
No, they were trying to find the algorithms teacher, I think.
But it's easy to find algorithms teacher. Should be easy.
For
There's
some
so
reason-
many of
Or maybe
people.
maybe it was not about algorithms.
Yeah.
By
but
the way,
okay.
which language do you use in your work? So which
English.
programming language?
No.
Program in English.
So Python I can program. So yeah, I
Nice.
wrote a grader in Python because it just for mathematical research I don't need
So
complicated
it's
things.
enough to
Yeah.
know Python
Because it's the best language in the world, actually. If Python was value semantics, it would be the best language in the world.
Better semantics.
Value semantics. Not
Value-
the Python uses reference semantics by default. If you know.
For mutable.
For mutable objects,
Yeah.
of course, for primitives it's value semantics still, but for mutable objects, and if there was a version of Python with value semantics for, I think it would be instantly best language in the world.
But it will be even slower, I think. Each time you have to copy all these lists, how can it work at reasonable speed?
So then they add pointer semantics and
C,
they
C,
get
C++.
Galang or something like that.
C++ uses value semantics and works fine.
I mean, you could pass a pointer.
Yes, you can do the same in Python. You could have you could have done the same.
Yeah, but copying lists is easy, but to brackets and double point if you want value semantics.
Yeah, I know, but
I agree. That's a lot of bugs because you changed something somewhere because you forgot. Yeah, okay, but we should work instead of talk. So just 5 or 10 minutes branching algorithm. So what did we achieve? So we had we already said 2 to the k n to the power c algorithm for vertex cover, and now we can put here 2 to the power k. But now let's think a little bit about this constant 2 here. So we can do better. It was the promise, and so there we will use 3 ideas. So so the first idea we already mentioned. So for if we pick a node, here is node of degree 3, and so here is more of the graph. Then we have two options. Either we put the node in the vertex cover, or if we believe the node is not in the vertex cover, then all its neighbors must be in the vertex cover. And so the first idea is, when we branch, we select a node with maximal degree. Because then, when we have a tree, we will have one branch will recurse with k minus 1, the other branch will recurse with k minus d. And so if we can guarantee that d equals 10 or something, then we know the second tree, the second branch will be 10 units shorter. But this happens recursively. So it will be exponentially thinner, or 3. And we will get a better constant. So what we will achieve is 1.46 or something to the power k. And this is cool, it's almost square root 2.
That's legit.
That means we get twice as big k we can deal than original thing. State of the art is 284 or something. I'm not sure about the last digit to the power k. So it means you can double another time. And it means that if k is up to 190, there is something like clam value. It's not so serious, but it gives some idea, like that's 10 to the power 20 operations. That's like the maximum the bus will pay for or something. At least already 30 years they say that this is kind of, it's one CPU year or so, okay, I don't know, or 5. So and then if k equals to 190, you're still good. If you have less CPU time, then maybe k equals 170, but that's pretty big, because we will see that the graph is at least twice the size. So if your inputs are a few hundreds, and then you can be lucky that there is extra structure, and it's worst case time bound. Okay, but so this is the goal for now. And as I said, we will combine 3 ideas. So first idea is pick the node with largest degree. Second idea, if our graph only has nodes of degree 2, we can compute the answer in polynomial time. So why is it? So if we only have nodes of degree 2,
we want to check what, once again.
what is minimal size of
vertex,
vertex cover? Yeah.
the minimal.
Yeah, minimal size
So
of vertex
vertex
cover
cover.
of degree 2. So how can we know it right away when all nodes have degree 2?
We have. We should check that the graph is a circle.
Yeah, graph is a union of cycles and paths.
Yeah.
And so for a cycle, it's easy to know the minimal size of vertex cover. So this is 5, 1, 2, 3, 4, 5. So what's the minimal size of vertex cover of this cycle?
4.
3.
3.
Yeah.
Yeah.
The second
Yeah.
one.
Yeah. So for cycle at odd position, but unfortunately one is covered twice, so we cannot avoid it. So if there's a cycle of even length, then it's precisely half we can use.
Yes. We can divide by 2 and round
Yeah.
up.
Yeah. Like here is 8. So then we select these in the vertex cover, right? For cycle, the vertex cover is half, and then for paths it's similar. I need to think. So if the length is even, then it's half of the length minus 1. And okay, I don't need to explain. It's for you, maybe to implement.
But what is if the graph is not a cycle?
Yeah, then it's a path. So if all degrees are at most 2,
Yeah.
then there are vertices, might be vertices with degree 1. They are endpoints of a path.
A graph is either a cycle or a path or a combination.
Yeah.
No, not a combination.
No, not a combination.
So we
Yeah,
look
you
to
have
all
either
connected
one.
components,
Yeah.
and each connected component can only be a cycle or a path.
Там же могут быть разные компоненты связаны.
Ну, тогда-
Дизъюнктное объединение циклов и путей.
Э,
Ну, блядь.
Yeah,
Okay.
you could have 2 cycles or
Yeah.
cycle and a path.
5 cycles on the
So
path,
you
yeah.
should divide them into.
Yeah, and then for each you compute
Mhm.
the. So then we're very happy if all nodes have degree 2. So that's good news because if we take maximal, so this is a kernel rule, like reduction rule for kernel. We've seen all nodes have degree 2, we output the answer here. And otherwise we have node of degree 3. And so this idea of selecting node with largest degree. So now let us bound the runtime and try to verify we indeed have this times poly x. Poly of length number of nodes. Okay. So then we need to make a recursive relation because we have recursion trees. So we start with argument k, and here we fix one node. Should I make an example, or it will be okay? Let's do example. Okay, so no, that's too fast. Something like this. Okay, so we pick a node of degree 3. Let's say this one. And then we put this one in the vertex cover. So we will have let's say we want the vertex
not the
cover of
largest
size
degree.
3.
It's not the largest degree. The largest degree is 4.
It is here, yeah. Okay. Yeah, but okay, let's say algorithm is pick a node of degree 3, then I don't need to redraw, of at least 3.
Okay.
So this is here. And so for k, let's choose, I think 3 will be enough, yeah. So, and then we have this and 2, and 1 branch. And for the other, we add these 3. And after we add these 3, then we only have these 2 bottom left. So we have this thing and 0, right? Because here we do -1, and here we do minus degree of the selected node. So here is phi.
Well, what did we do now?
Okay, so we're branching, and in the root, this is our instance in the root.
Yeah.
So this is the graph and the number 3. We pick a node, and
Mm.
then in one branch, we delete it. We put the node in the vertex cover, and here are all. This is what remains to be covered. And we used already 1 node, so here is a 2. And here we put the 3 neighbors in the vertex cover. So we decrease, okay, let's do 4, because otherwise here we already done. So then we will have 3 here, and we will have 1 here. And then we branch again. So we will pick a node of with degree at least 3. And then here we pick this node, so what's left is this, this and this, and 2. And on the other side we pick the 3 neighbors, and what is left is nothing. The 3 neighbors cover everything, right? So we have empty. But there is a small problem. We did subtract, so -1. So this is a false one.
Why? We did choose.
So we did subtract.
B.
Sorry. Yeah,
It
you're
would be
right.
0.
Yeah. Sorry, I'm wrong. We have 0. Okay, and here the same thing. So, okay, here are no nodes. Sorry, here are no nodes of degree 3. So we apply our algorithm. So we decompose in paths and cycle. Here is just 1 path, and we know 1 node is enough. So here it's okay. So if we go in the recursion in this way, then we are good. But actually, maybe it's more clever to go in the small branch first. I don't know.
So in the recursion,
Now I think about it in my solution of the programming exercise. I didn't think about doing it in this direction.
It seems like you have to check the small.
Yeah, because this is a much smaller tree. If it contains the correct answer, you might find it faster. Okay. So, so in the first case, we will go here and then see a path of length 4, which can be covered by 2 nodes. So this is the branching algorithm. And now we have to bound the runtime. And so note that here, each time we go to the right, the degree decreases by at least 3.
By at least.
Yeah. And so do you know how we can find a recursive relation for such unbalanced trees? Okay, then I will explain. So we will guess a power and then check that our guess works. So we need to think about the sizes of the trees. So, so here we have a tree. So that is called S for size. A size with k nodes. Here we will have, we want to bound the size of a tree for the value k minus 1, here k minus 2. So in the worst case we have exactly 3 nodes each time. And so what we want to find, we want to find a recursive relation in which sk minus 1 plus sk minus 3
But
plus 1, because we count the number of recursive calls.
3 here is maximum degree, yes?
Yeah, so 3 is the degree of the node
Degree of
Yeah.
of that node that is
that we picked, and we guaranteed. So we always pick a node of degree 3, and if there is no such node, we compute directly. So then we are in the leaf of our tree.
if all the nodes have more than degree 3.
Very good, and then we just pick any one of them.
Yeah, no.
Okay, so there are 2 variants. So what's clever if you program is to pick a node of maximal degree. But now I explained that we just pick any node of degree at least 3 for clean proof, and because I didn't want to redraw the picture. Okay, so what we know is that maybe here we have smaller value. Sorry, I want to say, now we want to find, so the inequality was wrong. So we want to have upper bound on the number of recursive calls. So what's the number of recursive calls? For a tree with k elements, it's the root plus the size of the 2 children. Okay, now we need to make a guess. And so we will say our guess is x to the power k. Sorry, first let us get to the rid of this plus 1. So I will define t equal to s t of k is 1 more than or 1 less than s of x. Sorry, 1 more than s of x. So then what we have here is t of k minus 1 is bigger than t of k minus 1 plus t of k minus 3 minus 2 plus 1. Okay, so you see why I changed from t to s. I want to bound s, but instead I will bound s plus 1. And if I do bound s plus 1, then it's nice because these minus 1 and minus 2 plus 1 falls off. Okay, now I can bound something nice. So now we simply guess, we guess a function t of k equals to x to the power k. And then we will think, what is this x? So note that 2 to the power k will work. And so what do we have here? 2 to the power k is bigger than 2 to the power k minus 1 plus 2 to the power k minus 3. But it's not a good upper bound, right? So someone is falling asleep. So yeah,
So it's like for 3
it's
hours
almost
today.
finished. Yeah, yeah. Okay. So But this is kind of a waste because we have a lot of, I mean, if we divide by 2 to the power k, we're just saying 2 is equal to 1 plus 1/8 or something, 1/4. That's stupid. We should put a better one. So let's put x. And then we have x to the power k, x to the power k minus 1, k minus 3. And then we divide by x to the power k minus 3. So that will give us x to the power 3, x squared plus 1. So we want to find the smallest x for which this is true, and then we have the bound on the size. And it turns out it's about 1.46. And so now we improved our algorithm, and we can deal with k twice as large. So before it's probably like graphs with k 70, now 140 or something. Just to give you an idea. So, and that finishes branching algorithm. Cool. To go to state of the art, you need to do more things. It's really cool. I found some movie. But okay, first step is get rid of nodes of degree 2. So that's the task for the programming project. Just find the rewrite rule where you get rid of nodes of degree 2.
And what?
So find the reduction rule to cut out nodes of degree 2. And it's also an exercise now. Okay, so lecture is finished and we can speak about the exercises.
And the seminar part is not
Is-
recorded.
Yeah. But it is streamed on how do I stop? Oh, did I stop live stream? Oh, but the student disappeared anyway, so... no. Yeah, sorry. Maxime. Yeah. So let us go to the exercises. Okay, so first exercise is give kernel for vertex cover. So previous kernel was size k squared, k times k plus 1. And now the size should be k plus k squared divided by 2. And the hint is, what should we do with nodes of degree 1 for vertex cover problem? So I read the question again. Show that the vertex cover problem has a kernel with at most k plus k squared over 2 nodes by creating a reduction rule for nodes of degree 1.
So degree 1.
I mean, we should delete them and their own
Yeah.
sibling
Yeah, exactly.
gets into the vertex
Yeah.
cover,
Yeah, indeed.
because it has more
More power,
Yeah.
it's more useful.
degree.
So just
I
solve
mean,
the
at
exercise.
least one
In the meantime,
degree.
I will put the screen so you can see the exercise. I forgot to print it.
Technological advantage.
Yeah, I'm a disaster with technology. Using my scripts for email to create programming exercise.
It should be at least a long email name, so nobody can randomly find it and send some code.
You should bring
But just in a few weeks I will it's just an email on some server. The problem is that like Yandex or something, they don't accept emails with code inside it because they think you're spreading viruses.
They're probably right.
One obviously can spread the virus.
What? Maybe it's better to rotate the display.
Well, but I can make it even bigger if I.
I see.
But somehow.
Control plus that?
No, it doesn't.
Maybe Control Shift plus.
Maybe click with the mouse.
Yeah,
Top
I know,
right corner.
but trying.
No, top right.
Yeah.
There is a percentage. Oh. Yeah, I mean this.
Fit.
It was.
Oh.
Now maybe Control plus. And it works.
That's too bit.
That's.
I should get rid of this.
Oh, that's good. Could you please turn the? Are we going to solve all of this?
No, the three.
But how to prove that it is k plus k squared divided by 2?
Yeah, that's the second part of the exercise. So you already did half. So what we know after this reduction rule?
We are lucky that there is only one home task,
Yeah.
but not for each of the lectures.
Well, this programming exercise, and then in 2 weeks also programming exercise, and then I've seen like some people they last year there were 4 students from software engineering, and I saw that people like to work between 2 in the morning and 6 in the morning, because I can see when the emails arrive. And they worked 3 what should I call mornings.
Yeah.
Well, one only submitted 2 times, so he worked like there is some test case until it worked. And so, but his solution I didn't like, because he used NumPy and my exponent was not powerful enough to. I did it just with lists, and he. Yeah, I need to check carefully what he did, but somehow. Okay, I shouldn't tell all this.
No, if we're not allowed to use NumPy, it's.
No, you're allowed to. You can do it.
Yeah, that's great.
It's just grader. I should try to find bigger instances or something. Yeah.
Yeah, because it
Yeah, the exponent
improves
yeah.
exponentially with vector operations.
Yeah. So and his constant was better, and then he got. There are like 3 instances. There are 50 test cases, and 3 of them are really hard. But just to check whether you do something even more clever than was supposed to do, then I want to know about it. So don't try to have 50 out of 50. So just be happy if you have like 90% of cases right.
Okay.
I mean, last time we did like a picture of like the maximum number of nodes, but now that doesn't work. because no, I mean this picture.
Да, давай поменяем
Yeah,
0 на
yeah.
1 и все будет.
No, no,
нормально.
it's the idea to use
Let's,
this.
let's exchange.
That's the right idea, but now we know something more.
I mean,
Drop zeros, drop ones.
Yeah,
so-
and that's all.
yeah,
That's all the
and
modifications.
all the under things are ones, so we can't use them.
no,
but
but
we
now
can-
we use the same idea, but now we
We
know
can
something
we
more.
can do this like
Что?
ну, типа так сделать.
Yeah, indeed, yeah.
And now there aren't ones, but
А,
I don't know how to say that this is the most like optimal.
Yeah, you count edges in two ways.
I don't know. I think that's
So you count edges from, okay, I'm saying the answer.
mm,
So you know every edge. So can there be edges
Yeah.
in the by the way, it's unrelated and irrelevant, but in the bottom we cannot have edges, right?
yes,
Correct.
yes.
We can
It
just
would
draw
be
we can
covered.
just draw a picture and that shows everything like
Yeah, I mean-
everything's connected.
Yeah,
And
like
so-
to the other nodes, but we can't say that it's like the biggest number of.
Окей, сверху,
I mean-
сверху К, снизу какие там нужно, чтобы было типа 2. Какое у нас накладывается ограничение на ребра? Сейчас, что спрашивают? К плюс К квадрат пополам. Nodes. Ща.
No,
Ну,
but
смотри,
it's no, it's k squared plus k, I think.
Yeah. No, well, it's slightly better. So just count the edges on the top. What's the maximum number of edges on the top? All edges go from top to
Mm.
bottom.
K squared
the maximum number of edges on the top is 0.
No, we can draw them. They would be covered.
Yeah. So indeed
But,
we have k squared edges.
Why,
I mean,
why do we
almost-
draw them?
Okay, and now in the bottom, how many nodes
Yeah.
can we have maximally? So there
K
are just
squared
k squared hands
I mean,
on the top.
We don't have a limit for edges.
No, but here it's a guy with at least two hands.
Yeah.
Maybe 3 or 4, but at least 2 hands. And here we have k squared hands. What's maximal number of guys we can have? If we know that they have at least 2
Okay.
hands.
At least 2. The maximal number of guys. K squared divided by
Yeah.
2.
Right, by
K
2.
squared by
Yeah.
2.
And so
That's it.
we just place k squared nodes on the top.
Yeah.
Maybe then in the task it should be written not nodes but edges, because
Yeah, сейчас.
K.
Nodes что-то.
No, I just k plus k squared. So what we had
Nodes.
before. K plus k squared nodes.
nodes, yeah,
And I wrote nodes, yeah?
yeah.
Yeah. And now we have
We
fewer.
can
We
have-
have k plus k squared over 2. And why it's it? Before, people only had one arm.
But
And we have k squared
we
hands on
don't
the
have a
top.
limit on arms. We have a limit on people.
We have limit on arms on the top. There are k nodes of
Why?
degree at most k because of reduction rule.
Ah,
Yeah,
at
forgot.
most
yeah,
K.
sorry, yeah. Let's
Wait,
check
can-
your.
Yeah. We can have at most k minus 1 divided by 2 edges, right?
Yeah, okay.
Is this correct?
Even better, yes.
It's edges.
Cool. Yeah.
And so we have
No.
Okay.
We can have the okay. So here you're saying that the guys should be different, but there can be
Yes.
a guy who gives 2 guys who give the same hands to the so the better bound. So we can. So you are assuming that every guy. So there are k guys with k hands, k monsters, let's say.
Yes.
Yeah. But it can be that a guy in the bottom chooses the same two monsters. So it's not the number of two monsters. The number of ways we pick two monsters.
Какой...
So you try to get this formula, and if you believe that it's forbidden for two guys to choose the same two monsters, then you're right. Then we need fewer people on the bottom. We can have a little fewer.
I completely forgot.
Okay,
what was the
I think that
reduction of-
you need to make
Yeah,
a
and I
proof
need to
first,
meditate a little
and
bit.
then.
on this.
But unfortunately, I think this is the best with current proof.
No, типа окей.
Okay. So the next we will skip because it's for you. Then the 3 is new problem. So input is a graph, and then the parameters will be k and d. And so the question is, can we remove k nodes so that all remaining nodes have degree at most d? So for example, let us say d equals 1 and k equals 1. And we take, as usual, this graph. Okay, so can we remove one node so that remaining nodes have degree at most 1?
Nope.
No. But we can,
Yes, and now we can.
yeah. So we can remove one node,
Right.
this one, and then remaining nodes have degree 2. Like this one is, yeah. So that's the problem. So now you need to make a kernel for it.
Что-то difficult to think already.
Yeah,
Need to go get some sleep.
Yeah, it is.
Here we should do some like recursion.
So, by the way, there was a hint. So when we said d equal to 0, we have vertex cover. So can we remove k nodes so that remaining nodes have no edges? That's the same as saying find k nodes that cover all the edges.
Find the vertex cover.
Yeah. So this is kind of hint that you should do exactly the same.
Ну, если там поднять до единички, то что тогда?
So you need to find some reduction rules.
With D1 it's easy. You just replace this with this. But you can't do that for D3.
Ну, подожди, в смысле, не слушай. Не понять вообще ничего.
I mean, если, короче...
Ну,
Нет, я не могу так сделать.
ты можешь, типа...
Только если у них изначально один дегри. Ну ладно.
When you remote them on yourself, each remaining node has a degree at most. Ну, если да 0, то это vertex cover. Мы знаем тогда, что делать.
Maybe we can do something similar.
We probably don't need the nodes that already have a small degree.
Yeah. Okay.
Respected.
I mean, there is indeed no harm, so I can already write it without knowing the rest of the answer. It cannot be wrong, this reduction rule.
Так, хорошо. Ну,
Logically, with a big degree, we should somehow
eliminate the node with the biggest degree, right?
Yeah, we should remove them, I think. But
Ну, нужно просто жадно как-то зайти. То есть убирать самый большой. We need to remove the node with the biggest degree. Check conditions.
Yeah, for the branching, but now it's about kernel. So it's a good idea. So which nodes shall we remove also?
Сейчас, подожди.
So remember, what did we do for vertex cover in the kernel?
So we took the vertex with the largest degree.
In the branching algorithm.
Yeah.
Yeah. But then in the kernel for vertex
Yeah.
cover, you remember?
we removed the degree k plus 1.
Yeah.
Can we remove k nodes? If we have a node with a degree more than k, strictly more than k, then what does it mean?
Maybe more than d.
If
More than d.
нет, k plus d, там, короче,
All the nodes already have more than d degree.
let me think a little bit. Здесь у меня сейчас сколько? Камень D. If we have a node with a degree more than, strictly more than k minus d, what does it mean? We have to put it into the vertex cover. For otherwise, we would have to get all this removed. Yeah, and it's more than. У нас там было, если d 0, да, то и тут типа k, вот так, то мы не можем, мы просто не можем его не взять. We can not
Yeah, you can speak in Russian. I understand a bit of Russian. So.
Короче говоря, если у нас было
And
как?
also, you have to solve anyway. So.
Если у нас было D0, типа в vertex cover, то мы не могли не взять чела с степенью больше k, потому что иначе нам
Да,
пришлось бы
нельзя.
взять всех вот этих остальных.
Да, но тут можно взять не все, а только k минус d. Да, вы правы.
Вот, сейчас, подожди. Давай теперь здесь, короче, если d не 0.
So actually, it's good to walk around because then blood goes to your brain.
Если k не 0, точнее d не 0, тогда что получается? Вот у нас есть чел, у него есть...
Не, мне кажется, нужно просто сделать, типа,
К.
спуститься до d0, типа, сверху вниз. Ну, типа, сделать...
Как спуститься до d 0?
Ну,
У
сделать
нас там пока
какой-то-
нигде d не...
или стоп.
У нас пока нигде d не уменьшалось вообще. Да? Ну что мы первый
Ладно,
сделали?
короче, ладно, ну, цель ограничить что-то с большой степенью.
Ну да, ну я говорю, нужно понять, что если... Да, сейчас.
Мне нравилось k минус d.
Мне тоже нравилось k минус d, но надо понять, что с ним делать. Если у него больше кентов, чем k минус d, то что это означает? Ну, типа, если мы уберем
То
их сейчас, нам же не надо ему 0 оставлять. Да, смотри, если у него больше,
надо оставить d.
сейчас, если у него больше, чем k минус d, то убрав k, мы ему оставим больше, чем d. Да, короче, если
Чего?
если у вершины, еще раз, вот допустим, у
А может не минус d?
Нет, почему не минус?
Что такое k минус d?
Может и плюс. Да, наверное, плюс. Типа, если у вершины больше, чем степень больше, чем k плюс d, что это означает? Если
мы-
мы удалим
то мы
k,
должны-
k штук,
Да,
то
должны-
мы не можем получить меньше, чем d.
Мы либо ее
А мы
берем
хотим
не
меньше.
два, либо берем все остальное.
Ну да, где они там, что там, блядь? At most d, да, короче,
Да, то есть, короче,
remove, короче,
если
все.
больше, чем k плюс d,
Ну, здесь
ну там плюс 1.
тег
Ладно.
больше
Да.
k плюс d, вот так.
Ну да, потому что иначе...
Мы тупо не можем их не взять, если мы их не возьмем, нам придется удалять все остальные.
Да.
Типа, ну, что бы мы ни сделали, у него будет больше, чем d. Ну, типа, окей, дальше. Что дальше? Что там третий шаг какой был? В предыдущем алгоритме.
Третий шаг был порезать все ноды.
Nodes with... И
А,
типа, если осталось больше какого-то, короче, и вот здесь третий шаг.
Ножницы нарисуй.
Что еще?
Ножницы нарисуй.
А нахер ножницы. If nodes больше. Сейчас надо понять только больше чего.
Сколько мы можем, получается, покрыть нашим ограничением? У нас
Мы
ограничение,
хотим, чтобы у них не больше, чем d. Смотри, не больше,
у
чем
нас
d.
ограничение лежит типа от d до там k плюс d, да.
Нет, подожди, почему? Вот на этом шаге, короче, в конце у нас у каждой вершины не больше, чем d штук. У нас k вершин.
Подожди, да.
Сейчас, подожди, или сколько у нас вообще вершин-то? Can we remove k nodes? N. У нас типа n, ну давай, правильно. N минус k вершин, что ли, или что? Да, сейчас вот надо понять, почему. А там у нас что было?
Там было
К умножить
К
на К плюс 1.
То есть, да, вот это вот как раз... а как будет выглядеть эта картинка с руками чувачков?
Ну
в
вот так.
нашем случае?
Ну, вот как. Сейчас. Типа, если у нас на этом шаге осталось больше, чем k плюс почему там было k на k плюс 1?
Потому что мы можем взять k. Да, мы можем. Сколько мы можем взять? Мы можем взять k. То есть k у нас будет в этом произведении.
А что мы вообще рисуем сейчас? Мы рисуем то, что мы уже взяли, или то,
Типа,
что осталось?
Мы хотим сверху то, что мы берем и удаляем, и что-то нарисовать вокруг этого, что остается.
Ну хорошо,
все остальное.
Ну, то есть сверху у нас всегда k.
Сверху, да,
всегда
сверху всегда k, да.
А теперь мы говорим, типа, сколько максимум можем сюда напихать.
Да.
С условием, что у каждой
может
не
быть-
больше, чем d. У каждой не больше, чем d.
Да, у каждой
Ну, то есть здесь d просто. Здесь d. K умножить на d. Ну, то есть сколько всего вершин? Всего вершин k умножить на k. Сейчас.
Ну
k.
да, ты прав.
Этих k, а здесь k здесь d.
Здесь
У каждой
KD,
d,
да.
kd, да, kd.
То есть,
Только k плюс, да, k плюс kd, то есть это k на d плюс 1. Вот так.
да.
Или если говорим, если больше, чем k на d плюс 1, то no. Все.
Ну да.
Думаю, что мы решили вопрос.
Ну, можно было оставить, можно.
Ну, сейчас я перерисую. Все стерто. Все, мы ready.
Good.
So what
So
can
first
we
we
do?
remove the nodes with degree not first row.
Yeah.
Then we remove the nodes with degree more than k plus d, and then if remaining nodes.
No, it's
K.
more than this.
K plus times d plus 1, because we have taken k
If it's
nodes
yes,
by now, and the maximum degree is d.
Yeah.
So the maximum number of nodes here is k times d, and so the total maximum
And then
is k.
0 degrees unit. Excellent. Yes. Great.
And we just
Well
followed
done.
the steps
Okay.
of the previous.
So Maxime, you agree?
Is there anybody there?
Yeah. Okay. Well done. So. So it's 2 before 9.
Let's go.
But for the next lecture, it's probably difficult to have exercise, so we can continue with this list
Okay.
because Maxime said, "Oh, you need to explain again to
Yeah.
Maxime." Yeah.
To be honest, I don't get it.
So you can
Ну,
say
давайте,
in
да,
Russian.
да.
Yeah. But you need to ask a question. Can you put on the microphone?
Или текстом.
Yeah. Yeah, so please ask a question, but you can type in Russian. The other students will help you.
Единственное, что мне кажется мутно, это вот это, я не понимаю.
Okay, so
Почему?
in the meantime, I can tell you that
Типа,
Тут все понятно. Типа мы можем на третьем шаге мы взяли, допустим, что мы уже нашли к чуваков. к этому.
это типа лучший случай. Да,
Ну,
это
да.
лучший случай
Это
для
лучший
нас.
случай для нас. Мы уже нашли
Да.
К штук.
Да, в каком
Сколько может быть вообще
максимально,
всего?
да,
Лучший
сколько
случай.
максимально можем покрыть. Да, это лучший случай.
okay. Yeah. No,
Maxim
there is time.
Decided to
yeah.
pass out. Or what?
No, he got it. Okay.
Nice,
Good,
nice
yeah.
man.
He heard you talking, I guess. And it's nice. Yeah, if you go over the presentation or the recording, then it should be clear. It's direct adaptation. So
Yeah, almost an hour passed.